Greetings and welcome to the complete lecture for Chapter 2 of Chemistry 221, and I'm super glad to have you here. In this chapter, we're going to look a little bit more beyond the mundane parts of Chapter 1, where we learned about sig figs and measurement and density and stuff. Important qualities, absolutely, but not as exciting as this chapter, because in this chapter, we're actually going to talk more about the atoms and the molecules and ions that made up to them. And we'll also talk a little bit about the history of how this all came around, which is kind of a fascinating story unto itself. So without further ado, let's check this chapter out.
If modern astrophysical theories of the origin of the universe are correct, in the first few moments of the violent birth of the universe, there were only two elements, hydrogen and helium.
So all of the matter all around us right now, caffeine, cell phones, our bodies, cars, etc., all of the matter, according to science, came from the Big Bang. And the Big Bang happened just under 14 billion years ago, so a long time ago. And at first there weren't any atoms at all, but then after a while they started making hydrogen and helium after that and stuff like that. We'll talk more about the Big Bang and how things started in a later chapter, but all of the matter around us originally came from this kind of event, which is pretty crazy. When you look at the cosmic universe, this is what they feel is the abundance of the elements. It's powers of 10 on the left-hand, on the y-axis, so you can see that they're different. But the biggest one of those lines is for hydrogen. So there's much more hydrogen in the universe than anything else. And helium follows. But then you'll see there's a gap. Like there is lithium, beryllium, and boron, but not as much. And then carbon all of a sudden appears quite relevant. A lot of nitrogen, but there's a dip, and then oxygen. So you can see that not all the elements are around at the same amount. Iron on the far right is going to be of interest to us in Chemistry 222, so you can check that out and we'll see why I made a highlight of it at that time later. But in the Earth, we talk about both the composition of elements in the crust and also in the atmosphere. And in the crust, which is the dirt and everything under us essentially, that's mostly silicon and oxygen. So geologists do a lot with silicates and stuff like that. In the atmosphere, most of our atmosphere is actually nitrogen and oxygen. And nitrogen is actually more abundant in our atmosphere than oxygen, which is kind of crazy. Oxygen's roughly 20% of our atmosphere. Nitrogen's roughly 80% of our atmosphere. So a lot more elements. So it kind of depends on what you're talking about as to which element is more abundant. The first person to create a credible, in my opinion, view of what the atom is all about was a person named Democritus. And he was a contemporary of Plato, one of the great Greek philosophers. So again, this is a long time ago, more than 2,000 years ago, that these people were sitting around campfires, essentially. And remember, they didn't even have like indoor plumbing and stuff like that at that time, but they were philosophizing as to the nature of matter and all kinds of other things. And so Democritus had this idea that the universe consists of the void, emptiness, and well as atomos, which now is translated into the word atom. And he thought that atoms have structure and volume. And if you took something like gold, which was something they, of course, cherished at the time, you could cut gold up and up and up into halves and halves and halves until you finally get down to the smallest unit of matter. And if you cut that, it would no longer be gold. And this is amazingly akin to what we use in chemistry, because if you split apart an atom, you no longer have gold, you'll have something else. And gold, this is supposedly a quote from him, gold can be divided into smaller pieces only so far before the pieces no longer retain the properties of gold. And you can see in this little comic book thing that I found on the right-hand side, "You're a fool, Democritus. All men know that this gold is one solid piece." And he goes, "No, I believe that everything is made up of tiny particles we cannot see." Now, it's very unfortunate that Democritus's ideas didn't go forward at the time. And at the time, Plato and his student Aristotle created the idea of earth, air, fire, and water. And that was actually chemistry for way too long. But anyway, that's just the way things go. Scientists were able to come back to Democritus' ideas, and they consider him kind of a hero now of chemistry. Then we're going to fast forward many years until we get to around 1804, and John Dalton proposed his atomic theory in that time. Now, John Dalton is considered a very important player when it comes to chemistry. Isaac Newton brought physics out into one kind of field and created that. Sometimes people think of John Dalton as the Newton of chemistry because he really brought chemistry into the modern world. John Dalton was a colorblind scientist, and so he had to people help him with colors and stuff, but he was still able to create some fantastic ideas. He came up with some important concepts. One of them was that matter's composed of atoms, which is kind of like what Democritus thought almost 2,000 years ago. But he also went on to say that atoms of one element are different from other elements' atoms. So like helium atoms are different than hydrogen, and helium would be different from lithium, stuff like that. And he proposed that there would be some scale to measure them with. And this scale is now based around what's called an atomic mass unit, an AMU. And you can see down there at the bottom that an atomic mass unit is a very small amount of mass, 1.66 times 10 to the minus 24 grams. Now, a pound of something in our macroscopic world, a pound is about 454 grams. This is many, many orders of magnitude smaller, so it's very small. And sometimes they refer to the AMU as a Dalton, gets the symbol capital D sub A. That's in reference to his idea for creating the scale, which is kind of cool. Compounds like water and sodium chloride, stuff like that, always have a definitive whole number ratio of atoms. And so water is always going to be H2O, 2 hydrogens to 1 oxygen, not 1 hydrogen to 1 oxygen or 2 oxygens to 1 hydrogen, stuff like that. And this was important. No one had really thought about that, but if you have a true compound, you have to have a definitive ratio of atoms, or else it'll be really crazy. He also proposed that atoms cannot be created or destroyed. And we're going to see that this is a realistic expectation most of the time, but not all of the time. If you're in the world of nuclear chemistry, you can actually transform one atom to the other. We'll talk about that in a future chapter. But the important part here is that, like say here at Mount Hood Community College, we don't usually go around creating or destroying atoms. So most of the time, what he stated here was correct, even though there are some fine-tuning kind of things to do. Through the work of lots of scientists, including people like J.J. Thomson, who had an initial idea for the atom, which was later debunked, as well as Marie Curie, who did a lot of work with radioactivity, they came up with this kind of model of the atom. And this did not happen overnight. It took lots of iterations, some trials and errors. But what they found, and what the current model proposes, is that atoms contain 3 types of major particles called protons, neutrons, and electrons. And the protons and neutrons are in the nucleus, in the center of the atom, and electrons are on the outside, that kind of shimmering stuff you see around the nucleus. Also important is that the glue that holds the atom together is basically around positive protons and negative electrons. Positive and negative charges attract each other, which is important, and that's one of the main things that holds the atom together. Neutrons are neutral. They have no charge at all. This is an overview of some exact values for protons, electrons, and neutrons. So protons are positive, and in science, charge is measured in what's called a coulomb. It gets the symbol capital C. And they've determined that one proton has a charge of 1.6 times 10 to the minus 19th coulombs. And that's a very small number under any scale, but it does represent the positive charge that's on a proton. Now, they've also been able to figure out the mass of a proton, and it's again very, very small, 1.67 times 10 to the minus 24 grams. Now, using a number like that is very unwieldy. So if you take that number and you divide it by the AMU, you get a relative mass of what's called 1.0073 AMUs. So this is just a little, the proton is just a little bit more than 1 AMU when it comes to the mass. So if you put it on a scale, an AMU scale, it would be just a little bit more than 1, and that'll be important for something coming up. Electrons are negative. So you can see the charge on the electron there, minus 1.6 times 10 to the minus 19th coulombs. So they're the same magnitude, but opposite charge. Protons are positive, electrons are negative. Now there's the relative mass of an electron, and you'll notice it's really, really small, 0.0005. So it takes hardly any mass and stuff to make up an electron. So while a proton is small, electrons are really, really small, much, much, much smaller than the protons that they come from. A neutron, on the other hand, has no charge, so there's no coulombs associated with it because it's not positive or negative. It would have a charge of 0 coulombs, I suppose. And the mass is 1.0087 AMUs. So you can see how, of the 3 particles, the neutron is the biggest. 1.0087 is bigger than 1.0073 for the proton. But both neutrons and protons are about the same mass. Neutrons are a little bit bigger, but they're about the same mass. And they're much bigger than the electron, which is 0.005486. So if you put these all on a scale, protons and neutrons would be about the same, and electrons would be much, much, much less than that. Here's the kind of question to see how you're doing with this information. It says place the 3 subatomic particles in order of increasing mass, so from the smallest to the biggest. And like we talked about in the last part there, the electron is much, much, much smaller than the proton and neutron, so it's going to be the smallest. It'll go first. And although protons and neutrons are both about 1 AMU, the neutron is a little bit bigger than the proton, so the best answer here would be answer D. Electron is smaller than a proton, and a proton is a little bit smaller than a neutron.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Rutherford is a fantastic scientist, and I could go a long time talking about how cool he is. But anyway, Rutherford actually came from New Zealand, and he went to England to study. And at the time, they thought that people from the colonies were inferior and not really worthy. But Rutherford worked really hard, and he came up with this idea for the gold foil experiment, which is still just an experiment that has rocked the chemistry world for a long time. And in that video, you could see how most of the alpha particles, which is a type of radiation, just went right on through. All right, no big deal. And everybody kind of thought that was going to be the case. They thought that atoms were big kind of amorphous things, and most of the time the radiation would go through. But sometimes the little alpha particles would reflect back, and they would go back and hit that kind of photographic plate around it. Sometimes they'd go off to the left or the right. And so, long story short, they realized that the atom must be very dense and very positive. And here's why. Alpha particles have a positive charge. And if the density of the highly dense nucleus is positive as well, then positive and positive is going to repel. So some of those alpha particles came back and kind of went to the left and the right, and some of them kind of reflected off to the left and the right, or refracted, I guess would be a better term. Anyway, it was a fantastic experiment, and nobody saw this coming, and scientists still talk about this today. So the gold foil experiment is Rutherford's big thing, and he discovered how the atom is actually very, very dense in the nucleus, and it has a positive charge, but most of the atom is quite empty. Here's another graphic kind of showing what's happening. So what happened, what Rutherford's results were here, is that in the left-hand side, the nucleus itself is incredibly small, all right? Like they feel that the atom is roughly, you can see there, 10 to the minus 10 meters across. So that would be the diameter. But if you look down on the kind of middle right, the nucleus itself, 10 to the minus 15 meters. So what that means is the nucleus is incredibly small. all right? And if it's incredibly small with all those protons and neutrons, which, by the way, have a lot more mass than the electrons, man, that thing is going to be super dense, and it's going to be positively charged because of the protons. So then in this upper part, the alpha particles are coming through like this. And again, remember, alpha particles have a positive charge. And most of them just go straight on through, no problem. They don't care at all. But boy, once in a while, when they get next to the nucleus, that's when they kind of go up and to the left, or some of them came back like that to the right if they had a direct collision. Nobody saw this was going to happen. So Rutherford's gold foil experiment still defines how scientists think of the atom. It's just that nucleus super dense, super small, electrons float around the outside, so most of the atom is empty, but oh boy, if you get to that middle nucleus, things start to happen. Most of the atom is empty space, protons and neutrons in the nucleus, and that nucleus is very, very dense. Electrons are in space around the nucleus. Now, here's another important concept. If you have an equal number of protons which are positive and electrons which are negative, the atom overall does not have a charge, and the atom is electrically neutral, all right? We're going to talk more about this later, but if the protons and electrons are equal, then we consider the atom to be neutral. Like it doesn't have a net positive charge if you have an excess of protons, or a net negative charge if you have an excess of electrons. And boy, oh boy, are these atoms small. And in the chapter 1 introduction, I talked about how a teaspoon of water has just a ton more molecules than there are teaspoons in the Atlantic Ocean. Well, because water is H2O, 2 hydrogens, 1 oxygen, 3 atoms, you can even say that this 1 teaspoon of water has 3 times as many atoms as the Atlantic Ocean has teaspoons of water. So just really small. All right, you can't get out your photographic equipment normally and take pictures of these things because they're so small. You need special techniques. Pretty cool stuff.
It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol.
I love these old science videos, but I like the idea here. If the atom was the size of the United States, then the nucleus would be 100 feet. So, wow, pretty small. Anyway, just kind of putting it in perspective there. Kind of cool. Here's a picture of 35 xenon atoms. IBM has been a real leader in trying to have pictures taken of atoms. And if you use your imagination there's an I on the far left, a B kind of in the middle, and an M and there on the right. And to manipulate individual atoms like that is pretty fantastic. They used to take this picture what's called scanning tunneling microscopy, STM. That's just one example of some of these new techniques that are being used to measure and take pictures of atoms. And there you can actually find on the internet little movies and stuff of them using atoms to move things around, which is cool. There's a website down there. If you're curious, you can look up more information on how IBM does STM to see atoms. But again, think about how small those are, because each of those little humps, those little mountains, if you will, is about 10 to the minus 10 meters, which is what scientists sometimes refer to as an angstrom. The A with the circle on the top is an angstrom. But the nucleus would be basically 5 orders of magnitude smaller, 10 to the minus 15th meters. We don't have cool pictures of that because that's still so small. But hey, we're at the atom, so maybe one day. I'm hopeful anyway. The atomic number, which gets the symbol Z, is an important characteristic of atoms. And what scientists feel is that if you have a big collection of, say, aluminum, all of those aluminum atoms will have the same atomic number. And the atomic number literally just means the number of protons. So if you see a value for Z, that's the atomic number, all right? And that means how many protons are in that element. So if you have 13 protons in an atom, that means you have an atomic number of 13. And that will always mean that you have aluminum, because aluminum's always 13. Now, if you happen to have, say, an atomic number of 6 or 6 protons, and you look on the periodic table, 6 protons would be carbon, because carbon is number 6. And if you had only 1 proton, it would be hydrogen, etc., etc. So, woohoo, you can now look up how many protons are in each element on the periodic table. Pretty cool. Now, because no one wants to spell out aluminum all the time, they usually use symbols for these things. Symbols on the periodic table, the first letter is always capitalized, and if there's a second letter, then the second letter is lowercase. So it's AL, it's not AI. Don't even go there. All right. In chemistry world, it'd be AL, not AI. And that always means aluminum, so you don't have to symbol it out. This guy Moseley was the first one to think about atomic number. He used X-ray techniques to figure that out. So a good periodic table will always have the atomic number, and it'll always have the symbol. And there's also something that good periodic tables have called the atomic weight. And we'll talk about that here in a little bit. But for right now, we're at least beginning to discern what some of those symbols mean on the periodic table, which is kind of cool. So the question might come, what is the atomic number Z of oxygen? All right, and first of all, you need a periodic table to answer this. And in class, I will definitely give you a periodic table, but if you can't wait for class, what you can do is go to mhchem.org/per-tab. This will be the periodic table that we'll use in class. And so if you look on that periodic table and you want to look up the atomic number for oxygen, what you want is that whole number right there. And if you look on the periodic table that I gave you, or your own periodic table, oxygen is number 8. That's where the O is. If you thought maybe it was the 16, that's the atomic weight, and we'll talk about that in a little bit. But for right now, we're looking just at the whole numbers, which are the atomic numbers, and that's how the periodic table is organized. So periodic table 1, for atomic number 1 would be hydrogen, and that's first, and helium, atomic number 2 would be second, lithium, atomic number 3 would be third, etc., etc. If the protons and electrons are equal, then you have a neutral atom, and that's happens a lot. However, we're going to see that often you can have a system with fewer electrons becoming more positive, or more electrons, which means becoming more negative. And so I'm introducing here some new terms. I want to introduce anion and cation. And what happens is an anion is if you have extra electrons. So your atom has gained one or more electrons, it becomes negative, and scientists call this an anion. And we're going to see that a lot of times the elements, if they are an anion, if they have extra electrons, they get an IDE ending. Now, on the other hand, we're also going to see examples of when atoms have lost electrons, so they have more protons than electrons. Those positive ions are called cations. If you call it cations, it's okay, but it's officially cation, all right? And so in the upper right-hand corner there, you can see how sodium, we're going to see, likes to lose an electron. And so when it does, it goes from 11 protons, which is the atomic number for sodium, by the way, and a neutral atom would have an equal number of electrons, 11 electrons. It goes from that to 11 protons and 10 electrons. So it's lost an electron. And by losing that one negative one, now you have 11 positive charges and 10 negative charges. So overall, it becomes a positive 1 ion. So the sodium cation is sodium plus 1. Under it is chlorine. Now, chlorine's number 17 on the periodic table, so that means 17 protons and 17 electrons. And we're going to see that chlorine likes to gain an electron. 17 protons are still there, but now there's 18 electrons. So if you do some quick math, it's like 17 times positive 1 for the protons, plus 18 times negative 1 for the electrons. That leaves an overall negative 1 charge. So chlorine likes to be negative 1. It becomes a chlorine anion. And if you want to get technical, we're going to see that a lot of times that chlorine anion is called chloride. So the IDE can sometimes tell you that you have a negative charge. Now, if anion and cation are new terms to you, which is totally cool, just remember here, which is kind of silly, cats have paws, so cations are positive. Yeah, I know, I need a real job or something like that, or stay out at night, whatever. I need something, all right? But anyway, cations are positive. I don't have a cool expression for anions being negative, but you get the idea. There's the chemistry meme cat. We'll see that once in a while. I kind of have a weakness for those. They're so silly. But anyway, here the cat is saying cations are positive. And if you're a dog lover, I apologize. Now, another important part about an atom is what's called the mass number, and mass number gets the symbol A. And usually the mass value, by the way, is in atomic mass units, the AMUs we talked about earlier. So atomic mass units can be added together for the protons and neutrons to find this value. Remember, the electrons are so small, it takes like 2,000 of them to make an AMU, so we usually ignore the electrons when it comes to masses. So here's an example of a boron atom. This boron atom has 5 protons because, again, if you look at the periodic table, boron is number 5. But this one also has 5 neutrons. So the mass number, which is protons plus neutrons, would be 5 plus 5, or 10. And this symbolism right here is used a lot to represent these different atoms and what they have. The left-hand side of the element symbol, there's a lowercase and an uppercase number often. The lowercase number is Z, the atomic number. So boron on the periodic table is 5. That's why the 5 is there. The upper left-hand corner represents the mass number. So since this is boron with a total of 10 AMUs for a mass number, we would put a 10 up there. So upper left is the mass number A, lower left is the atomic number or number of protons Z. And why they do this is that we're going to see that every quadrant, every corner of the element symbol has something in it. Here's a helium example on the right-hand side. This is a helium plus 2, so it's lost some electrons. That would be the charge then. So the charge goes in the upper right-hand corner. But we'll talk about all of this later on. And if you're curious, okay, yes, the lower right-hand number will represent the number of atoms. So we saw, for example, water was H2O. That 2 goes in the lower right corner. Ah, the joys of being a chemist. Now, where this becomes really interesting is because boron actually doesn't always have 5 neutrons. Sometimes boron has 6 neutrons. So these are examples of what are called isotopes of the same element. And all elements on the periodic table have this. So it's the same number of protons. That hasn't changed, because if you change the protons, you change the element. If you, for example, added a proton to that boron 10, it would become carbon, because carbon has 6 protons. So we're not doing that. Atomic number of protons stays the same, but the number of neutrons change. And this creates what's called an isotope. And isotopes are really important. So down there below, you can see here's boron 10 that we looked at earlier, no problem. And this is boron 11. So boron 11 still has those 5 protons because it's boron. But if it has a mass number 11, then 11 minus 5, it must have 6 neutrons for it. So you can always find the number of neutrons. You can take the mass number, in this case 11, subtract the atomic number, which in this case is 5. 11 minus 5 is 6. If you did it for the boron 10, it would be 10 minus 5, or 5 neutrons. And again, all elements have at least one other somewhat dominant isotope running around somewhere with it. Some of them have many, many, many isotopes, more than 50, say. Kind of crazy.
Now, within each element or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes.
So isotopes they used here as an example of family. Sometimes I've used isotopes as an example of ice creams. Like you can have chocolate ice cream, vanilla ice cream, strawberry ice cream. They're all ice creams, but they do have different properties. And we're going to see that the isotopes of a family can have different properties as well. Here's an example of a problem you might see. It says how many neutrons are in manganese 55. All right. And if you see that dash 55, the dash 55, that's the mass number. That's the mass. What mass number is protons plus neutrons. So to answer this question, you need to look at a periodic table and figure out, first of all, what element manganese is. Spoiler alert, manganese has the symbol Mn. So if you look on the periodic table, it's number 25 on the periodic table. So 25 means 25 protons. So 55 is protons plus neutrons. 25 is the number of protons. So 55 minus 25 will tell you how many neutrons there are. Should be 30 neutrons inside there. So you can see the utility of the periodic table. It helps you with atomic numbers, if nothing else. You can find neutrons then inside it, and this will have important values coming up. Here's an example of hydrogen, which has 3 main isotopes, and all 3 isotopes are around us all the time, especially the first 2, but a little bit of the third one as well. So hydrogen is number 1 on the periodic table, and that means that the atomic number is always going to be 1 proton, which is right next door, and that doesn't change. But what does change for the different isotopes are the number of neutrons. So hydrogen 1 is called protium. It has 0 electrons to it, all right? Because remember, top number minus bottom number equals number of neutrons, basically. Protium has no neutrons. And most of hydrogen, i.e. 99.989% of it, is this protium. This is water we drink, the ice cubes, etc., etc. However, there is a significant amount of the second isotope, which is called deuterium. And deuterium has 1 neutron plus 1 hydrogen for a mass number of 2. All right. So hydrogen 2, or deuterium, is this thing. Now, it's about 0.01%, which is actually enough that it shows up in our water. Remember, we're dealing with just massive numbers of atoms at one time. If you've heard of heavy hydrogen is deuterium, all right, and they'll do some kind of cool things with it. Notice the glass of water up above. If you make an ice cube of pure D2O, so this is hydrogen, but it's deuterium, it's so much more massive that it sinks, all right? We said that densities, the lower densities go to the bottom, lighter densities go to the top. Well, heavy water, D2O, is heavy enough that it actually sinks to the bottom. Pretty crazy. Now, there is a third isotope called tritium. Tritium has 2 neutrons and 1 proton. Tritium is actually radioactive. You don't want to have a round of it at any one time, but although there is some, it's a very, very small amount. They just put trace right here. So you don't have a lot of tritium. If you take a big drink of water, it's okay, but there is enough around that you can do some interesting things, and we'll talk about this in a future lecture. They determined the masses of the isotopes and things like that using something called a mass spectrometer. And a mass spectrometer is a really cool thing. You inject a sample right here on the left side, and it essentially vaporizes it, turns it into a gas. And then you ionize the gas sample, so it usually then has positive charges. And what they do is they use magnets. And the magnets, as you'll see in physics, or maybe you've seen it already, can manipulate the curve of the positive ions. So they constantly manipulate the magnet in order to see like what things come through to the detector there, that kind of square thing at the end. And then the results of it here on this graph will show you. So for example, in this graph, there's a lot of the 20 isotope. This is a neon isotope, but there's a little bit of 21 and a little bit of 22. So this is how they determine then that there are isotopes. It's an amazing thing, this mass spectrometer. In organic chemistry, you'll probably use it if you take it. Pretty cool. There's a great video, by the way, if you want to look up this YouTube reference that talks about mass spectrometers a lot more detail than we will. A lot of elements only have 2 isotopes, though. So like here's an example of boron. You can see there's boron 10 and boron 11. Notice that the boron 10 is a lot less abundant than the boron 11, and we'll talk about that in a second. Likewise, here's an example of chlorine. There's a lot more chlorine 35 than there is chlorine 37. And there's implications for this. This is why I'm pointing it out. At one time, for about $50,000, you could get your own mass spectrometer and gas chromatography device. I have no idea how accurate that is anymore, but woohoo! You too can do mass spectrometry in your own home if you so wish to. All right, I'd like to, but you probably don't want to. Atomic mass is the third part on the periodic table. And in that video earlier, they called it atomic weight, but it's really a mass because weight has gravity, blah, blah, blah. Anyway, atomic mass is the last big thing we need to talk about what that means. And it has to do with the isotopes. So as we talked about earlier, boron can come in boron 10 and boron 11. And in that mass spectrometry slide I just showed you, it's roughly 80% boron 11 and roughly 20% boron 10, all right? At least on the Earth, as far as we know. One day maybe there will be more implications of this. So the atomic mass you can think of is the average mass of all the boron ever seen, all right? So what you can do, and this stems from math, is you can find the average mass based on how abundant they are. This little nomenclature is a little bit weird, but what it means is, first of all, you add up all of that's the summation sign in math, and you want to add up all of the abundances times the mass of that value. So for example, in our system, we have two values. We have two values of I, and one of them is for the boron 10, and one of them is for boron 11. And the abundance is usually just the decimal version of the percentage. So 20% would be 0.20 and 80% would be 0.80. So if you wanted to find the average mass of boron, you could do this quick little math, and it comes out to be 10.8 AMU. And this 10.8 number is the atomic mass. It's the third thing that's on the periodic table. So a good periodic table will have the atomic number, so you know which number it is. It'll have the symbol for the element. And the third thing now is the atomic mass. And they all stem from the averages of the abundances and how many isotopes there are. This handout right here, the isotope abundance handout, we'll talk a lot more about this. And it's in your companion and it's online. If you can't find it, let me know. Check that out if you need some more details about how this works out. Isotopes give some crazy values sometimes, but it's nothing you can't do. So lithium has two main isotopes as an example. 7.5% of the time you'll have a lithium-6, and 92.5% of the time you'll have lithium-7. So if you wanted to know the atomic mass of lithium, you technically don't need that information at all. You just look it up on the periodic table, and it's 6.941. So the atomic mass comes from the periodic table. I'm trying to confuse you here with numbers and blah, blah, blah. You don't really need it. You just look at the periodic table to get it. Now, how they got that 6.941 was they took the 6 of lithium, multiplied it by 0.075. They divided 7.5 by 100, and they added that to 7 times 0.925. And to better sig figs, you can get 6.941, but you get the idea. Now, for silicon, you can do the same thing. And so silicon has all these different isotopes. But again, the number that's on the periodic table for silicon, you can look it up. It's about 28 or so. They got that by taking the atomic number times the percentage in decimal, and they added it to the other two systems to get it right there, and you're good to go. Silicon on the periodic table is 28.086. That's just a number you look up, but that's where they're getting these numbers. All right, it's all based on it. Now, notice that in the first one, the average mass was about 6.9, all right? And that's much closer to 7. That's because most of the mass is lithium-7. So the average will always be closer to the higher abundance isotope. And in silicon, it's the same thing, that 28.086 or whatever the number was. Most of the silicon is silicon-28. More than 90% of the time, that's what you've got. So that's why the average mass is closer to silicon, stuff like that. Here's an example of a problem you might see. Here's an element. It doesn't exactly say what it is, but element 72 is 54.5% of the time abundant, and 73, 15.6, and element 70, the number 74 there, 29.9. What's a reasonable atomic mass? So the best way to do this would be to take 72, the atomic number, and multiply it by 0.545. Like you take those percentages and and divide by 100. And you'd add that to 73 times 0.156 and add that to 74 times 0.299. And if you get all that, you'll get one of the answers down there. Now, if you look at those numbers, there's a lot more 72 than there are 73 or 74. So it's going to be something around 72, but only half of it, I would guess off the top of my head, it's probably answer B. But when you do the math, that's the best way to do it. Definitely going to be answer B. Here's another problem. Nitrogen has two main isotopes, nitrogen 14 and nitrogen 15. Notice the abundance. The one is almost 100, but not quite 100%. The other one is almost, but not quite 0. It's barely 0.5%. And it says calculate the average atomic mass. So again, what you do is take that AMU mass and multiply it by the percentage divided by 100. So 99.6299 becomes 0.996299, and 0.3701 becomes 0.003701. So we do that over. It gets some weird math, but it comes out to be 14.0068 AMUs. That would be the number on the periodic table. That's how they calculate these things. Now, here's a question you might run into. Gallium has two main isotopes, gallium-69 and gallium-71, and you can see the masses there. The average atomic mass, i.e. the value from the periodic table for gallium, 69.723. You can use this information to calculate the percent abundance of each isotope, and this works as long as you only have two isotopes. So what we're going to do to solve this is we're going to set it up similar to what we did in the last problem. We're going to have the average, which is 69.723, equals the mass of the first one, 68 whatever, times its percentage. So X here is going to be the percentage of the 69. And we're going to add it to the mass of the second one, that 70.9 number, times the abundance of the other one, which we'll call Y. So you can see right now we have two unknowns, X and Y. And those are the two percentages of the gallium-61 and gallium-71. And those are tough to solve. However, the two abundances together have to equal 100%. Or if you're talking about them not in decimal version, 1, which is 100% in decimal, 1 equals X plus Y. So what you can do then is have one of them, we'll say Y, equals 1 minus X. If you subtract X from both sides on that last one, you get Y equals 1 minus X, and you're good to go. So what we're going to do in a little bit is we're going to substitute this part right here, the 1 minus X, we're going to substitute it up here. Then we're going to have one equation with one unknown X, and you can solve for X, and at the very end go back and go 1 minus X to solve for Y. Now X and Y are going to be decimal percentages, which you can multiply by 100 later if you'd like to. So here's the math involved. Here's that Y we talked about, and Y just equals 1 minus X. Now, at this point, I would really like you to try to solve this yourself, because algebra is all something you have done before, but maybe it's been a while, all right? And if it has been a while, this is just a good way to kind of remind you. When you have 1 minus X times that 70.9 number, you use what's called the distributive property to figure it out. And so what you'll do is you'll first multiply 1 times 70.9. You'll end up with positive 70.9249. But then you're going to go minus X times that. You'll have minus 70.9249X. So this is the joy of the distributive property. If you do all this and you do it correctly, and you have to get the X's on one side and the numbers on the other side, and then divide the X number by both sides to get X by itself, you end up with 0.6012, which is 60.12%. And then because Y equals 1 minus X, 1 minus 0.6012 gives you 0.3988 or 39.88%. So see if you can do this by yourself, okay? If you get stuck, call me in. Go see the Learning Success Center, the AVID Center. They can help you out too. But this will be an important skill going forward, that you know how to use this distributive property, solve for X, all that kind of stuff. And by all means, there's no shame if you don't remember, because this isn't something that a lot of people do every day. So reach out to me or the LSC AVID Center. People are here to help you, definitely. Here's another thing with isotopes. Antimony is another element, has a symbol Sb. There's two main isotopes, all right? And the average atomic mass of antimony, 121.76. And the question is, will you ever have one atom of antimony with 121.760 AMU? And the answer is no, you aren't, because you're going to have 120.9038 antimony 57-ish% of the time, and you're going to have 122.9042 antimony about 42% of the time. But you'll never have an atomic mass, one atom with 121.76. And remember, this is the number that's on the periodic table. And if it's a fake number, you might think, what the heck? All right, why are the chemists including this number on the periodic table? Well, the final answer is that we deal with so many atoms at one time. We're not talking about one atom or 10 atoms or 100 or 1,000 or a million. We're going to talk about just billions upon billions of atoms. And this average mass number is a great way to talk about all of the atoms of antimony together. But if you had a big bag of antimony and you pulled out one atom, you'd never have an atom of 121.760 AMUs. You'd have one of the other two masses, 57% or 42% of the time. This number is statistical. So in the lower right-hand corner right here, I have a silly graphic, far side, I think, and it shows, have you met our 1.5 children? And in Oregon, there's supposedly 1.7 to 1.8 kids per family. Now, that's an average in the state of Oregon. And you're never going to go to a house and see, 7/10 or 8/10 of a kid. That's gruesome and morbid beyond even my weird science fiction perspective. However, when you think of all the families in the United States, and in Oregon, so in this case specifically, that's more reasonable, because sometimes you'll have only one kid, and sometimes you'll have two kids, and sometimes you'll have 0 kids, and sometimes you'll have like 5 kids, right? So the average is important, and that's where these numbers come from. So the 121.760 is an average, all right? You don't have any individual antimonies at that. But when you're dealing with tons and tons of antimony at one time, and we will be, that's where this number becomes really important.